We will continue with the analysis. This analysis is useful because once you do, later on if you develop any algorithm, this same analysis has to be done. Okay, same in the sense like just few changes are needed. So it's worth doing this once, and then it's very similar stuff. Okay, that's how people write a lot of papers. So I will continue with this initial set of lectures. So Lipschitz continuity I have defined where gradient is bounded, right? But a very basic definition of Lipschitz continuity is, so let f from Rd to Rp. So it could be a vector valued function, right? So it's multivariable vector valued, and let us say some constant L greater than 0. So we say that f is L Lipschitz. Okay, if it satisfies f of x, norm of f of x. Okay, let us say for all x, y in Rd, norm of f of x minus f of y is less than equal to L norm of x minus y. Okay, so this is called Lipschitz continuity, and what we have used before is that the gradient. So this is equivalent to saying that the gradient of f, if f is differentiable, then gradient of f is bounded by the constant L. Okay, so in case f is differentiable, okay, so in case meaning gradient exists, then we can write an equivalent statement L greater than 0, then f is L Lipschitz if and only if the gradient of f is bounded for all x in Rd, the domain, the norm of the gradient of fx is less than equal to L. Okay, so this is useful when f is differentiable, and this is useful when it's very generic. Here I never used any gradient of f, right? So this is more generic. Okay, so we can prove this statement, okay, that this implies this and this implies this as well. Okay, if f is differentiable. So if you want to prove this one, so let us assume that f is Lipschitz by the original definition. Okay, so let us prove the forward implication. Okay, so let f be L Lipschitz, and so we are supposed to prove this now. Okay, so let f be f this, and then let x be in Rd, then we show that norm of the gradient of f x is less than equal to L. So let us first prove this part. Okay, and remember how norm was defined, right? This is norm of f and of grad of f, right? Grad of f in this case is what dimension, right? If f is Rd to Rp, let us say, okay, I wrote the same d here, it's Rp. So if f is from Rd to Rp, what can you say about grad f, right? What would be the dimension of grad f? What is the grad f dimension now? If it's 1, then what was the dimension? If it's real valued, then gradient is a vector, right? Vector of length d, right? So, but in this case I have p, right? So now it will become a matrix, right? So if we consider vectors as column, then it's d by 1 if its p is 1, and in the general case it's d by p. Okay, so this is a matrix, and we are looking at norm of a matrix. So it must be some induced norm, right? So we have defined some matrix norm before, and the way we define it is we look at the action of a matrix on some unit vector, right? So this we look at supremum over u, where norm grad f x applied on u, okay, divided by u transpose u. Okay, so the norm of a matrix is defined by action of the matrix on u relative to increase in u, right? So we have done that. So this is a induced norm, right? So this is a matrix norm which is induced from the norm. So I can also write this in terms of norm. So it seems that they have not cleaned the duster. Duster still remains dirty. So this is what how you measure a size of a matrix. Okay, norm is a measure, right? So then you apply it on u and see how much stretch or contraction it does to a u relative to the u, right? So another thing we can do is rather than saying that u is all possible u, it is enough that we check it is enough if we check how f acts on u which is on unit sphere. Okay, so what we are trying to see is what does the matrix grad f does, okay, on any u, okay, whether it stretches. So grad f u is whether it's this, so relative to u how big of stretching it does, then the norm is bigger and so on, right? But this could also be done on a unit sphere itself. We don't have to do it for all u. Okay, it's enough that I restrict my vectors where norm of u is 1. Okay, that is enough because I don't have to do it for all possible u which are here, whatever, right? It is enough because at the end of the day only direction matters. Okay, direction matters, and the u that are on the unit sphere, that is enough. Okay, so in this direction whether it will stretch more or whether in this direction it will stretch more relative to this vector, right? So that's why it is enough that we look into this norms where, so we can also look into this, right? So if norm of u is 1, then this means that this goes away. So then it is enough that we look into these norms, right? The supremum of these norms, right? Okay, so it's enough to look into grad f acting on u where u is on the unit sphere. Okay, that's what this norm means, right? Right. So if now we are supposed to use this and then prove this, right? So let us use directional derivative. So we keep this here, and let us use directional derivative. So which is df of x in the direction of of some vector v, and we have defined this before. This means t going to 0 plus, and f of x plus tv minus f of x by t in the direction of v, but for our purpose we could have taken u, because if I look at that, right, so sometimes I use d f, sometimes I use grad f, okay, both are same, okay. So yeah, the notes I am using is using d, so let us do d everywhere, because in future we might get confused, right. So let us replace everywhere by d. Okay, so we are here, right, and our goal is to prove this. So we took this, and we see that this is defined in this way. Okay, so basically it's action on some vector u, and this, when we take this and apply it on u, this is exactly the directional derivative, right. So the dfu is a directional derivative which is defined like this. Okay, this is how you see this will be used now. Okay. Okay. So now we will take the norm, because that's what we want, right. So taking norm, and using the fact that f is L ellipsis. So if I take a norm, then this is df of xu, and this, yeah, everywhere it's u, right. This is also u. So if we take a norm, then yeah, so we also have a norm inside. So it's limit t tends to 0 plus, and f of x plus tu minus f of x by t. So we have a norm that goes inside, and now we use the ellipsis property that fx minus fy is less than equal to this. So this guy is less than equal to limit t tends to 0 plus, and this is less than equal to L of the difference. So this is x plus tv tu minus x by t, and this is equal to limit t tends to 0 plus. Now x gets cancelled, t comes out. T was positive because it goes to 0 from the positive side. So t is positive, so it comes out, and we have and u was norm 1, right. So the u remains inside the norm, so it was 1. So x goes away, t comes out, so I have LT norm of u by t, tt goes away, and this is 1. So eventually we have L. Okay. So what we have proved is that dfu is less than equal to L, and this is what we are supposed to prove, right. So if this guy is less than equal to L, so this guy is less than equal to L now, right. So df is less than equal to L. So for all u, so obviously the supremum is also less than L, right. So this is the forward claim, right, where we have that f is L ellipsis, then the derivative being less than L is satisfied, right. Now we can do it the other way. Now let us assume that the derivative is bounded, and we will show that it's L ellipsis, right. So let us show it the other way. Now it is this implication. So assume now that norm of dfx is less than equal to L. Yeah, kind of we can change the variable, let us say, to z. Okay, for every z, for all z in Rd. Okay, so now we assume the bound on the gradient of f, and we are supposed to prove this. Okay, so that's why we choose a z, so that it does not interfere with this x and y. So, and we claim that, so now we will claim that f is L ellipsis. So fix, in this case, x comma y from the domain, and use, what are we going to use, right? If you recall something from calculus, then there is a result that kind of involves the function values and the derivative, right? So if you recall calculus, then what is it that involves difference of function values and derivatives, right? Do we study something like this in calculus? So if I have a function AB, right, and then we have FA and I have FB. Oh, it looks like the same place, right? Let me do it a little bit so that there is a FB. Okay, so what was it, that calculus result that relates FA, FB with the derivative F prime? So F should be continuous for that to work. So it's called the mean value theorem. So there is a special case of Rolle's theorem. The mean value theorem says that FB minus FA will be, and divided by, I want to find the slope, right? So divided by A minus B or B minus A. So FB minus FA divided by B minus A is equal to F dash of C, where C exists in AB. In Rolle's theorem, they would assume that FA is equal to FB, but that's fine. Like, this is a general case. So what this is trying to say, the mean value theorem, what this is trying to say is that FB minus FA and divided by this guy, right? So this will be the slope, right? So FB minus FA divided by A minus B. And I am supposed to divide by B, right? So basically this, right? This kind of slope I expect, right? So height divided by the length, okay, is essentially this divided by this gives you some slope, right? So what mean value theorem says is that this slope that you have, FE minus FA divided by B minus A, will be achieved by so there must exist some C where this slope will be same. Okay, so that's the C, and that will exist that will exist because it's a continuous function. Okay, so it must be that because of the continuous. If it was not continuous, then things can go wrong, but if it's continuous, then this is the slope that you have. It must be that the function at some point will go like this and then take also this. It may go up again, and it may go down again, but the fact that f a is here, f b is here, and function is continuous, it must be like this at some point, like this at some point, and then it increased here. In this case it was decreasing, but it must be like this. So this slope must be achievable, right? That's what mean value theorem says. And in a slightly more advanced case of that, we may say that it's less than equal to supremum of all the derivatives that you can get, okay, in a very relaxed, I can relax this more, okay. So I can say that fe minus fa by b minus a is less than equal to the maximum possible slope you can have, okay. So this is something I'm going to use now. I'm not going to go with the proof of this generic result, but there is a reference. I will give this as an exercise for you to go and see the check the proof. Okay, so we will use that, okay, and use the mean value inequality. So this is now called inequality, okay, mean value inequality. To write norm of fy minus fx is less than equal to supremum. So it's a very generic thing, okay. So here we said equal, but then there are some strict conditions that it's continuous and so on. But in the generic case, I can say at least it must be less than equal to the supremum of all possible derivative I can get. So this is supremum of z in xy df z y minus x. Okay, so this is not just mean value theorem, but it's a mean value inequality. Okay, so that's how we kind of we want to go there, and we have already the bound on which is part of the assumptions, right? The bound on dfz is there. That's part of the assumption, right? On the first line, it's already assumed that dfz is less than L. So now we can see that this guy is less than equal to L, and the z happens only in the supremum. So this is like less than equal to L, y minus x minus y, or y minus x is the same thing. In the norm it doesn't matter. So we have already proved this, right? So since norm of, so I should not write this again and again, right? Just make a reference to that, right? So this is true for all z, right? And this is, let us say, some star. So from star, now it is evident that norm of fy minus fx is less than equal to supremum over all L, but L is independent of z. So this is just finally is this, right? And this is what we were supposed to prove. So this is more general, but if f is differentiable, then both the definitions coincide. Okay. Now we will discuss something called strong convexity, okay, and then we will go to something called PL condition, which is an even more generalization of convexity. Okay, so we kind of want to generalize, right? Convex is a very special case, right? It has to be ball shaped. So some of the extensions or advanced optimization methods, they want to generalize. Okay, so what more generic relaxations I can give, and still I prove convergence, right? So that's where we will do that PL condition. Okay, but before that, I will define something called strong convexity, and the diagram is that we have convex sets, we have strongly convex sets, and this is all part of today, and this is called PL condition. Okay, so this is convex, this is strongly convex. So obviously strongly convex is inside convex, so it's a rather special case, But what is interesting is that some part of this is in PL which is outside both. So it's just called PL condition, okay? So P and L are initials of two mathematicians, okay? So we want to go there. So we first do strong convexity. So let f from Rd to R, we can put infinity also, it won't hurt, okay? But although we know that infinity means like useless. I mean, especially if I add the indicator functions, right? So that's when it makes sense, right? Because indicator functions are defined like that, right? So we can keep infinity and mu greater than 0. So we say that a function, we say that f is mu strongly convex if for every x comma y in the domain Rd and for every t in 0 1 we have mu t1 minus t by 2 x minus y whole squared plus f tx plus 1 minus ty is less than or equal to t fx plus 1 minus t fy. Okay. So what you can notice from here is this guy, right? This guy is something extra from the convexity, right? Convexity was only this, right? But then in mu strongly we are saying that even if I add some positive quantity, right? This is positive quantity, right? T being between 0 and 1 and so on, norm being positive. So we are saying that there is a little bit of leverage, right, between these guys, right? So function is not just above the curve values, but also kind of there is a good margin that it's above. Okay, so from this you can say that linear functions won't be mu strongly convex because linear functions are function values are exactly the line values, right? So linear functions, if I have a function like this, then it is certainly not mu because f function values is exactly equal to the, so this is my x, this is my y, and the generic points are function value and line value match, right? So this is exactly equal. So there is no way that I can add something positive. So linear function is an example that it does not have any possibility of being mu strongly convex, but in general for any other cases we may have a strong convexity. Okay, so as you can see, this is stronger than convex. Okay, so if this happens, then certainly if I remove this, then this becomes even lower, right? So certainly this inequality does not get violated if I remove this. So this means that strongly convex is necessarily convex. And yeah, so mu is greater than 0, right? So these guys are all greater than or equal to 0. Okay, so we are adding some positive quantity, and mu is the strongly convex constant. Mu is called strongly convex, a strong convexity constant. Okay, convexity constant of f, strong convexity constant of f. Okay. So one of the natural thing is if I have a convex function, can I make it strongly convex, right? What am I supposed to do to make it strongly convex? So then this next result tries to answer that. So let f from Rd to R, okay, and mu greater than 0, the function f is mu strongly convex if and only if there exists a convex function g from Rd to R such that fx can be written as gx plus mu by 2 norm x square. Okay. So what we are trying to say is and this is if and only if, right? So what this tries to say is that given f is convex, then there must exist gx, so that I can write gx plus mu by 2 this, and also the other way around. Okay. If g is convex and if I add this, then f necessarily becomes mu convex. Okay. So it's both ways, right? So this is a good result, because in some cases I may want to regularize my problem. So this is the regularization term, right, to make it strongly convex and maybe get a better convergence guarantee, right? If this regularization does not create any issues in my optimization problem and the result that I will get, right? So this is a good result which will be used a couple of times. So what I will do for today is that I will leave this proof for the moment. I will take this as a helper function, go ahead with other things, and when I will have time, I will, in the end, I will just prove this, come back and prove this. Okay. So proof is not that difficult, but it will take time. Okay. So what I will do is that I will leave this as a lemma, and I will try to at least complete the PL part today. So another lemma. So we can, for our purpose, we can use this. We can call this lemma as A. Okay, and this lemma as B. So if f from Rd to R is a continuous and strongly convex function, then f admits, in fact this lemma also I have to skip, because this lemma I may have to skip for several classes, because this lemma needs a little bit of topology, a little bit of things like lower semi-continuity and so on. And why this needs, first let me complete this, and then you can say why is this, right? So then f admits a unique okay. So this is a simple looking lemma, right? You can say that, oh, I already know this, right? F is convex, in fact strongly convex, so necessarily convex. Then f does admit a unique minimizer, right? We know this, right? But for which cases we know this? I mean, we know, I mean, intuitively we know, right? It's a ball shaped. So convex functions are ball shaped. So in fact they have a unique minimizer, right? But then why I am saying that this is not easy to prove? So what was the assumption that we used in the previous cases where we proved this?
Local minima exists.
No, I mean,
Prove uniqueness.
yeah, minima exist also. Still,
We never proved uniqueness.
uniqueness we can prove immediately, but we will need additional thing. In fact, we prove this, but we will need additional. What is first order convexity? First order, the name itself says first derivative is needed. General convexity result and prove unique minimizer. That's a little bit, but what we know, right, is fy greater than equal to fx plus grad fx y minus x. First order convexity first order convexity, we assume that f is differentiable, right? So a more generic proof, what I'm saying is a more generic proof is needed, okay, where you don't assume differentiability or anything, right? Yeah, in the differentiable case also we may not have shown uniqueness. We have shown the minima, right?
Local is a global. We showed that.
We have shown that local is a global, right? Right. Yeah, but in general, yeah. So even if, yeah, there can exist multiple here, right? Okay, but local becomes global, and that's when we assume the differentiability. Okay, then it's very easy to prove, right? We have proved this already. And why? What is it here that gives you uniqueness? What is extra here that can give uniqueness? So let us say I give you strongly convex here also and first order, right? So the uniqueness should follow there, and the proof is still easy for uniqueness there. First order convexity here, it's a little bit tricky. Okay, so because I will not assume even first order condition here, I would like to prove it with, I would like to prove this as a raw statement. Okay, so it's some generic strongly convex function, and from the basic definitions of strongly convex, basically this is what is given to you. Just this is given to you, not the first order convexity, because that requires differentiability. This is given to you, and using this proof that it admits a unique minimizer. So I'm going to leave this as well, but I will do this for sure, because this is part. Okay, so proof later, because I will prove it in a generic case which requires some idea of topology, coercive functions, lower semi-continuity. Okay, so it's so we leave this proof for the moment, and we take it as a fact that this is this admits a unique minimizer. Okay, and one of the ways to say that the reason why it admits a unique minimizer, right? Graphically, how do I explain this, right? Let us say proof is different thing, but strictly convex means it never becomes flat basically at any point, right? And non-strictly convex means that it could be like this, all differentiable, whatever. Okay, no problem. Okay, but here I may have multiple minimizers, right? Not unique. Strictness gives you uniqueness. Okay, it does not allow you allow the curve to become flat at any minima. Okay, so strongly convex means this, and because of the mu, okay, and we can also make an argument with the second order convexity, and that tells me that the Hessian in the normal convex case it's greater than equal to 0, meaning some eigenvalues could be 0, and in the strongly convex, in fact mu is greater than 0. Strongly convex says that it will be greater than equal to mu, and mu is itself greater than 0. So meaning the eigenvalues of Hessian are strictly greater than 0, meaning there will be strict curvature to be expected, not like this. This is happening because some of the eigenvalues can be 0. Okay, that's where you can get a flatness, but then eigenvalues being strictly greater than 0 means that your curve cannot become flat at any point. That's what strongly convex, I keep saying strictly, but it's strongly convex. Because of this mu is greater than 0, okay, and because of this, there is a way to prove also this, that the eigenvalue, so there is a second order condition as well, right? So we can do that, but for the moment I leave this proof because uniqueness and all this requires a little bit of more setup that I will leave for the moment. Yeah, strongly we had this strict, right, inequality.
In strictly,
Yeah, we had strict inequality, right? Yeah, so strictly convex meant this strict inequality, right?
yeah.
And that again gives me a leverage to have some mu for which I can add these terms. No, this is also a form of strict only, right? Because mu is strictly greater than 0. No, I guess because of this, right? It will never allow intuitively, right?
No?
We will not prove this, right?
Strictly also.
I mean, strictly is strictly is included here in some sense, right? Because if I have some positive term here, then if I remove this,
Yeah, strong implies.
no, that's the point, right? If I go with the intuitive explanation, then yeah, I mean there is a complete proof of that. We can do that, and in this case as well, as I said, yeah, strictly does imply or yeah, I mean strongly does imply strictly. So proof is for the strongly convex, so that's documented. Strictly, in the strict case, I just have this strict inequality, and if I can produce some mu again, in that case I believe I can, right? Because mu can be arbitrarily small. So if there is a strict inequality, then there seems to be a gap between this and this, which allows me to introduce this as well for a mu small enough, which needs maybe proof, okay, but it seems that I can put this term and it becomes strongly convex as well. Okay, so there is a leverage if there is a strict inequality. So constructively, how we will do that? If someone gives me strictly convex, then is there an existence proof that there will exist a mu for which?
There won't.
What was the example you gave?
I mean,
Hyperbola, or yeah, we may have to bound the domain somewhere, right? Okay, but it may not be. Yeah, in this case, it's unconstrained, right? But under certain constraint, yes, maybe. So what was the explicit function we said? Fy is fx is 1 over x.
x square minus 1.
No, just one dimensional, right?
Yeah, minus of under root x square minus 1.
Minus of
Under root x square minus
under root x square
minus
minus 1. So this goes where?
asymptotically to y equals to x at the bottom.
At the bottom, right? And this will be like this, right?
No, the other way around.
Or the other way around. This seems to be from the circle, right? One of the quadrants. Y is,
It's y square minus x square equals to this.
so this is like y square
Minus x square.
minus x square is 1, right? Like this, right? Okay.
I'm not
This is what you mean?
no.
So at x equals to 0, we, oh,
Y equals to 0, x equal to 1. 1 comma 0.
x equals to 0, it's not defined.
1 comma 0.
1, it's 0. 1, it's 0.
Vertical tangent goes to
So help me plot this quickly. So 1, it's, so at 1, it's 0. And let me do it more. Okay, so at, is it like this? No, but this is negative, right? So it should be below, I guess.
it's below.
So that's what I drawn, right? Mirror, right? Then it's not convex also.
No way.
If it's negative, then mirror about x, right? Anyway, like you figure this out then. I mean, which one, right? It cannot be this because it's negative value. So
Also with the balance.
x between 0 and 1, this one, right?
If x is between 0 and 1, it's not defined.
Yeah, I mean strictly between 0 and 1. Oh no, even that is not defined. Sorry, this is not defined. So it must be maybe on the negative side, maybe then.
I'll go back.
Minus, no, it doesn't work over there. Okay. Anyway, yeah. So it will be good if you can, yeah. Okay, so strictly convex, and but for strict convexity there is a proof about the unique minimizer that we will do later. So we will use this for the moment. Okay, so then we have lemma C, which says that if f from Rd to R is mu strongly convex and differentiable, then for all x and y, Fy is greater than or equal to Fx. So we are trying to extend this first order condition, but then again we have a leverage that we will have one more term, right? So everything same plus one more term. So this is grad Fx y minus x plus mu by 2 norm of y minus x squared. Okay. So up to the second term is a first order condition, and then this is the additional term that I have. And this is for mu strongly convex. So we can prove this result. So since f is mu strongly convex, there exists a g for which fx is gx plus mu by 2 x square, right? So we are going to use that and do some little bit of manipulations. Okay. So define gx to be fx minus mu by 2 norm x squared. Okay. There will exist some g according to this, which will be convex. Okay. So g will be necessarily convex. So according to lemma B, g is convex, not strongly, but but convex. And it is also differentiable, so we can have the derivative as well. So, and grad f x will be grad g x, and this is mu by 2, and I mean 2 gets cancelled, so just mu x, right. So, that is the gradient. All this we are going to use it here. Now, we will use convexity of G. Okay. So, let us use now convexity of G. Okay. So, using convexity of G, what is given is f is mu strongly convex as well. So, we can use convexity of G, and that will be the first order convexity that is written in the top right corner, and then we can substitute in place of G f, because this is what we are supposed to prove, right. This is something we are supposed to prove. So, and we are with G being convex, it satisfies that. We put the value of G then there, and from there we will derive this. Okay. So, using the first order convexity of G, we can write in the same way. So, G y is greater than equal to so, it is good to note in which form we want, right. In the form we want is y minus x, right. With the grad f we are supposed to get that. So, it is in good form, and then we get in here we will somehow bring in grad f also. Okay. So, now substitute in place of G y f x minus mu by 2. Okay. So, in this case it will be f y, right. So, f y minus mu by 2 norm y squared, right, and then this must be greater than equal to f x minus mu by 2 norm x squared, plus gradient also we know in terms of f. So, gradient of G is gradient of f minus mu x. Okay. So, and with this we are supposed to get to the result now, and this is true for all x and y in R d. Okay. So, everything follows for all x and y. So, let us do the rearrangement and see what is required. Okay. So, f y greater than equal to f x, and this guy goes there, the norm y. So, f y is greater than equal to f x plus mu by 2 norm y squared minus mu by 2 norm x squared, and let us extract this term from the norm, I mean the inner product, grad f x y minus x minus mu x x. Okay, we split the inner product. Okay. So, what are the things that are there? And so, f x I can see, and grad f x y minus x also see, and the relative terms are these with mu, right. So, let us do this rearrangement, f x plus grad f x y minus x, and then what is remaining is plus mu by 2 norm y square minus, let us put this. So, it is like 2ab form, right, mu x x, in fact not 2ab form, but yeah, It can be, right, because there is a y minus x. If I take, oh, there seems to be a mistake I have done. The mu x should not go with just x, right? It should go with y minus x, right? It's linear only in one of the arguments, right? The inner product. Okay, so mu x, y minus x. That's what is, I was wondering why it becomes a norm x square, right? And this guy, right, minus mu by 2. Okay, so this guy becomes, so it seems like we are supposed to get this xx somewhere, and this minus becomes plus mu by 2, because 1 x is inside there, 1 norm x square is inside, right? So minus mu by 2 norm x squared. So we need to do this splitting and simplify for x. I mean, why should I write this again and again, right? Just focus here. I mean, this guy, right? So this guy, we split it again, right? So this is mu by 2 norm y square minus mu norm x square. And let us keep it minus only, and then mu xy, and then we have mu by 2 norm x squared. Okay, so this mu by this one and this one, right? Oh, how come it should be have been plus, right? So this guy is minus, minus becomes plus, right? So this becomes mu by 2 x squared. So this is now of the form, seems to be of the form 2ab, right? So this is mu by 2 norm y square minus mu xy plus mu by 2 norm x squared. Okay, which becomes the last term, which is mu by 2 y minus x whole squared. Okay, so this is, so if you want, you can take the mu by 2 common, and this is of the form a square minus 2ab plus b square in the inner product form, right? So we could have done this as a mu by 2 common. So this is 2, and this goes away. So this is exactly mu by 2 norm of y minus x, or x minus y is the same thing, whole squared. Okay, and the remaining terms are the same, and that gives us the proof of this lemma C. Yeah, it is L2, yes.
Only for L2.
Yeah, this you take it as L2. Okay, because otherwise we don't know. You're right. So this is L2, and L2 is like x transpose x. So then we can take the derivative. Yeah, yes, we are taking 2.
There also it's 2.
Yeah, there also is 2. Yes, when I'm not saying it's 2. The usual vector norms are all 2. Okay, without specifying, they are by default 2. In general, you cannot say, okay, one norm non-differentiable. Okay, in fact, many other norms are not differentiable. Infinity norm not differentiable. L2 norm is the good one, right? Okay, so by default, if I don't put 2, you on a vector, then it's 2 norm. Now let us go to something which is called PL condition, and that gives you a more leverage, okay, beyond convexity now. Okay, so we kind of now generalize in this advanced course, right? We get into something called PL conditions, and many new papers, including neural networks. So if I'm working with neural networks, in some cases like MLP, they with some activation function, they satisfy PL condition. Okay, so then you can extend this solvers for deep learning kind of. I mean, I should not use deep very quickly, but yeah, in certain cases with nice activation and so on, you may do it in some cases. Okay, we will try to do that as well, but let us build in a step by step. So this is called PL condition or Polyak, and this is another name which is very difficult to pronounce. Okay, so it's like L is silent. Okay, so Ozjazvik. Okay, that's what it's called. L O J A. It's like Slavic name. Okay, East European. S I E W I C Z. Even memorize. So that's why people call it just PL. Okay, it's much easier to call it PL. So what is this PL condition, right? Let us see this, and how does this generalize convexity, convex arguments, right? Convexity. So let f from R d to R. So let us focus on real valued, be differentiable, and mu greater than 0. We say that f is mu PL if it is bounded. So the function f is bounded from below, It needs lower boundedness because it compares from infimum. Okay, we will see this. So bounded from below all the problems we consider in optimization problem are minimization problems by default. Okay, because maximization problem is minimization of the negative of the f. So that's why we don't. So bounded from below is a good necessity, right? Because otherwise there will be minima will be infinity, and that is useless. Okay, so bounded from below, and if for all x in Rd, fx minus infimum of f is less than equal to 1 by 2 mu norm grad fx squared. Okay, this is the Polyak PL condition. It's called PL condition. Okay, so it's good to stare at this, like what exactly is trying to say, right? It's saying that the function value at x, the jump in function value at x. Okay, so this the jump from the lowest possible value of f, of the current fx from the lowest possible value of f, is bounded by this, which is the norm of the gradient. Okay, so the jump that you have should not exceed the gradient, but it's quite general in the sense that you are allowed to have mu very close to 0. So in some sense you can make it as high as possible and kind of necessarily satisfy this in many cases. Okay, because mu you are allowed to be what this is trying to say is that quite a good amount of jump can be accepted. Okay, in general we don't like functions which are we have very sharp jumps. Okay, so that's why we have bounds on Lipschitz continuity tells us that gradient of the function is bounded, meaning the function is well behaved. It does not go suddenly like this up, and so that's why we need a good behavior in the function. So we say that, but here it's a PL condition, right? So here it says from its lowest possible value fx is bounded by the gradient. Okay. Okay, so let us see the consequences of that. You may maybe play around with some function plots and so on. I will give you an exercise to prove that a function satisfies PL and but not convex and so on. So what is to be noted is, so it satisfies this, and we say that, we just say that f is PL if there exists mu greater than 0 such that f is mu PL. And we specify mu PL when it is associated with this mu, right? So in general we say it's simply PL if I can find a mu for which this is like mu PL. So this condition is like a mu PL because there is a mu for which the PL is satisfied. Okay, so it's the same thing. Just, I mean, usually it's kind of like you can ignore saying mu each time. Okay, but in the hindsight you have the knowledge that there is some mu for which the PL condition is satisfied. So PL condition is weaker than strong convexity. Okay, so PL property is weaker than strong convexity. Weaker means more general. A condition being weaker means that it's a general property. It's more generic. It applies to wider set of functions. It's more relaxed. Okay, so okay. So we can prove that. Okay, so how we will prove that? If something is strongly convex, then it's necessarily PL. Okay, but otherwise it's not true, and that will say that PL is even more general. Okay, so let us try to prove this. Lemma C we had, or now we have D. So let f from Rd to R differentiable and mu greater than 0 if f is mu strongly convex, then f is mu PL. Okay, so basically this proof should work. Okay, if that is the case, okay, then strongly necessarily implies mu PL. Okay, so let us see that. So let x star be the minimizer of f, and that will kind of tell us the infimum. So let us prove this. So let x star be a minimizer of f such that is infimum of f. Okay, so multiplying, let us say, we are supposed to use the strongly convex argument, and strongly convex, yeah, so I will prove this. X star is a minimizer, and then in place of y maybe we can use y, we need a less than equal to sign, right? So yeah, x minus fy. Okay, so we put the fy on the right. So fx minus fy, and y we take it as x star, let's say. Then we get fx minus fx star, which is the infimum, and those guys on the right we can move it here on the left, and then we are supposed to somehow get grad fx. Okay, so we are supposed to get grad fx. Okay, so let us start with this lemma C. So f is strongly convex, then we do have this, and in place of y, at least in the first step, we have in place of y we are going to put x star, and that's how we will get the infimum of f. Okay, and okay, so let us do it here itself. So we are going to use this. So let y be x star. This was lemma c, right? So let us say in lemma c. Then we have, so let us do that 0 greater than equal to fx. So I move this y there, right? Fx minus f, and in place of y I put x star plus gradient of fx, and y is x star. Mu by 2 okay. So what to do next, right? And we can simplify this a little bit. We move this there, and this is the infimum, right? So I rearrange now, okay, just to organize a little bit. So this is fx minus, this is infimum of f, right? Because that's the point where it found the infimum, right? Infimum of f is less than or equal to, and this is negative of that, right? So negative of grad fx x star minus x plus mu by 2 norm x star minus x. Somehow we are supposed to prove this, right, on the right hand side. Okay, that doesn't look to be the case, right? Mu term should also be negative, right? Yeah, mu should also be negative. So is it possible that we will get this grad fx, or do we need to, sometimes we do a trick, right? Add or subtract. So what are the tricks we are going to do? This is simply a trick only. So one thing is that let us put this inside. So the minus in front doesn't look nice. So this is x minus x star these are like algebraic tricks, okay? So sometimes like you may have to stay here for several hours and it works, okay? So let us see. So we need to do the squaring, I guess. Squaring, like another way to say is like, okay, if I remove this term out, right? So what are the adjustments I am supposed to do? Or in other words, this is what I want, right? So why not add and subtract this? So sometimes these are the tricks you do. We need in x, right? Okay. Yeah, x minus star is same as x. X star is constant here. Yeah, that's that could be done also. But I mean, you see, when you are solving these convergence results and so on, you know for sure that you are going to prove PL condition, right? So what you do in that case, you just add and subtract. Okay, this is like a very, I mean, if you are thinking that okay, adding, subtracting, I mean, just from here extracting this may not be always easy, but sometimes what happens is that you add and subtract this, and you leave the term this is positive, and then the negative term somehow like you play around with the existing one, and maybe it's something negative term that I drop and still it remains positive. Okay? Some kind of things like that. Okay, we do. So let us see what we can do. But it's possible. Okay. So let us try the trick that I said. Okay, let us do add and subtract and see what happens. Okay, so I mean, we are increasing our difficulty, but by adding and subtracting. Okay, sometimes it may not be like if this add or subtract term is very big, then it makes things more scary also, right? So the question is, where do I fit this negative 1 by 2 mu grad f x? Where should I fit that, right? So I have a feeling that it might get into the form a square b square. So I see this term a square type, kind of 2ab type, and this is like a b square type. Okay, so I will put them together for the moment, and then do further simplification. So let me do the a square term, put the 1 by 2 mu norm of grad f x squared and plus grad f x x minus x star, and then minus mu by 2 x star minus x, and then the guy that we want, we keep it safe here, grad f x. Okay, so all our focus is on this. It seems like I should take the negative, because if I have negative of some positive number, then dropping that will keep it less than equal to. So that makes sense, right? So I will take a negative of this as a second step. So make it negative, this guy becomes negative, and this guy becomes positive. Okay, so whole focus goes here. Now I have to square this somehow, so that this becomes a necessarily a positive quantity and overall a negative quantity, which I can drop and keep the less than equal to sign. So now do you think I can square this? If that is the case, then what is that square, right? What is a and b such that it will be norm of, or a minus b, it does not matter, norm of a minus b whole square. Then what is a and b? That is what I am looking for. Yes, let us do that. That is a good idea for clarity, okay, because we will see 2ab here. So 1 minus 1 by 2 mu, let us do that. Then we are left with 2 mu here. Okay. So 1 by 2 mu. So 1 by 2 is there, but mu is in the denominator, right? So now we are supposed to put a square there. So this guy becomes mu squared. Okay. Now it seems of the form a minus b whole square. So a is like grad f, and b is like mu x star minus x. Okay. So it is of the form minus 1 by 2 mu norm of grad f x minus mu x star minus x whole squared. Okay. So that's of this form. You can check that by doing this transpose with itself, and you must get back this. Okay. So this is like grad f x. Okay. So there will be f transpose with itself, that will give you norm f square. There will be this guy mu x star minus x with itself, that will give you this, and there will be cross term that will be staying there as a inner product. Okay. So this guy is necessarily negative. This guy is necessarily negative, and the remaining term we have is just copy over here. So grad f x squared. Now I am safe to drop this because this is a negative term. So dropping a negative term makes this less than equal to 1 by 2 mu grad f x square. Okay. So proofs in optimization methods are very, very fun. This is one of these, but you will see, I mean, these are very tractable, what I want to say. From time to time you will need some a little bit of advanced maths, but a lot of algebraic manipulations are there. We will see in the coming courses as well. So you can publish a lot of papers like that. So I can do one more where you can see how PL condition can be used in kind of like neural network as well. Okay, so I do have some time. So let us do this result where PL condition is used for nonlinear model. Okay, So I can leave one exercise for you. As I said, I don't give homework, but I write exercises right on the board. So at the end, I will see who has done how many exercises, and I will give assignment marks. Okay. So there is no deadline. The deadline is right at the end. So you must compile your assignments and show me towards the end of the semester. So I will write this assignment for you. So let ft, this is a little bit long proof, but you try. Okay. In fact, this is long. That's why I'm not doing it. But you can try sine t whole squared. So this function, the first step is easy, that it's not convex for sure. Second derivative test you can do, and it's not necessarily positive for all t. Okay, but it satisfies PL condition. Okay, and so this is the exercise. Okay, so that ft is not convex, but f is PL. Okay, so this is an exercise you can try. It's a little bit tricky. At least the first part you can do. Okay, so the half marks you can get easily, but the second one is a little bit tricky. Okay, but it's simple algebra only. Okay, I mean, it's not like you will need any advanced maths or something. It's just simple algebra. So if you can do that, you can get this proof. Okay, so inequalities basically. So now let us see how PL condition looks like. Okay, in some cases. So example, so PL for nonlinear models. Okay, so what are there any, so if I take any specific function, right, and specific loss functions, which let us say I usually see this in deep learning, some L2 loss is taken. Okay, but the function is nonlinear. So how does PL condition look like? Okay, so that's the objective of this. So PL for nonlinear model. So let us define a loss. Okay, so we call it fx, and this is L2 loss. So phi of x minus y squared minus y whole squared. So this could be your let's say hypothesis, phi x, and y is the level you have, and you want to minimize this, and phi here is a nonlinear function. Okay, nonlinear. Okay, so how will PL condition look like? Okay, in this case, so where by nonlinear I mean you can use some perceptron here. Okay, so if you are familiar with perceptron, you can think of that. So phi from R d to Rn is assumed to be differentiable. Okay, is differentiable. So as you can say, now that the moment I say differentiable, then you are left with kind of smooth activation functions. If this is a perceptron, then go with sigmoid, tan h. Okay, so these are differentiable. You are not allowed ReLU, for example. Of course, we can see PL condition in the non-smooth case as well. There is a PL condition, but for the moment, let us assume that this is differentiable. Okay. Then what is this result? So then f is PL, I mean specifically for this kind of function. Okay, phi x minus y and phi is differentiable. Then f is PL if d phi transpose x. Remember, phi is a vector, right? Because the output of phi is n dimensional vector. So that's why we have this d phi transpose x is uniformly injective. I will define what it means. Okay, uniformly injective, and this means is that there exist mu greater than 0 such that for all x in Rd, lambda min of d phi x d phi x transpose is greater than or equal to mu. This is the definition of a map being uniformly injective. It's uniform in the sense that it's true for all x. That's why the uniformity comes from. Okay. So we can talk about lambda d because this is a matrix. D phi transpose is a matrix, and it's a square matrix because it's of the form A transpose. Even if A is not symmetric, A transpose is always symmetric. So this will be real eigenvalue. Hence we can talk about ordering. So it's greater than some number. So only real eigenvalue will be there for symmetric. Okay. So in that case, we.
So what is phi transpose x? Is it same as phi x transpose?
Which one?
D of phi.
Yeah, this is phi x transpose, because phi itself is a vector Rn. So phi x will be some n-dimensional vector. So either we can write this vector as column or as a row. So once we fix some convention, we stick to that. Okay. So what is the implication of all this? Okay. So what they're saying is then f is PL if this is uniformly injective. Okay. So and the uniformly injective condition is given to us, which means that the lambda mean must be greater than or equal to mu. Okay. So what are we supposed to prove, right? We are supposed to prove that if this happens, then f is necessarily PL. Okay. In other words, can you prove that the lambda min of the d phi transpose being greater than or equal to mu, then the function is necessarily PL. Okay. So essentially this is one way to characterize, okay, proof if it is easier for you to compute lambda min. Okay. So let us try to prove this. So this is our assumption now, and f is PL is our claim. Okay. So so f being PL, it's like fx minus infimum of f must be greater than less than equal to 1 by 2 mu. This is what we are supposed to prove. So let us start with the grad f norm of grad f square, and we will prove that it's greater than equal to 2 mu fx minus infimum of f. Okay. So let us start with grad f square. Okay. So we have norm of grad fx squared is equal to, and so if we take the gradient of f, right? So if we take the gradient of f that we need here, then it will be grad f phi, and then so it's like a chain rule, right? The grad of phi and then this itself. Okay. So if we write that, then this is d phi transpose and then phi x minus y. Okay. So this is what we have, and this is squared. Okay. So grad f x squared we have to do. So this is grad f x, we put that, and we are somehow supposed to use this, that lambda mean is greater than or equal to mu, and all this should lead me to less than greater than or equal to fx minus infimum. Okay. So how I am going to, from here, how I am going to use this, right? So how do you see this? Yeah, because I just put grad f value here, the outside norm still remains, right? Yeah. So how do you connect this with this, right? Half will get cancelled, I guess, right? Yeah, half gets cancelled. Okay, that's just this part. Half gets cancelled, so these guys are there, and then outside we have this norm. Okay. So I think I have done this before. What does lambda mean of a matrix means? Okay, in terms of Rayleigh quotient, right? I think I have done this. So let us try to recall. So lambda min of any matrix A is infimum over U of X transpose, sorry, U transpose AU by U transpose U. So the minimum eigenvalue of a matrix A is an optimization problem. Okay, so basically you take infimum of this U transpose AU divided by because, and the U for which this will be achieved will be your eigenvector corresponding to smallest eigenvalue, because by nature eigenvector tells me that it's the smallest stretch that I am going to do in that direction, right? So that's a very good intuition that only the smallest eigenvector will give me the relative scaling which is the least, and the other counterpart of this will be lambda max, which will be supremum. So the largest stretch that can be created is along the largest eigenvector corresponding to the largest eigenvalue. Okay. In fact, you can prove this rigorously, but for the moment we can use this. So in place of A we have this guy, right? So lambda min of this being greater than equal to 0 means that that this ratio, okay, is greater than equal to mu. If this ratio is greater than equal to mu, then how do I connect this, right? So then to connect this you have to see what exactly, I mean you have to expand this norm, right? Norm squared, right? So norm of x square is x transpose x. If you do that, then you get something like that, where your u will be chosen in a way that it's phi x minus y, and u transpose u that you see, that will be phi x minus, so norm of phi x minus y. Okay, so it seems like more or less things are set up here. If I expand this, then I do see it in this form, u transpose AU, okay, where u is phi x minus y and A will be d phi transpose d phi transpose. Okay, so let us try to work with this. I hope I'm not missing anything. So yeah, it should come out. Let's see. 6:30 was the end, right?
Yeah.
So I'm certainly certainly going beyond. Okay, but this should be completed quickly. So this is lambda min d phi x transpose. This means infimum over u of u transpose d phi x transpose u by u transpose u, and this we are said that this is greater than equal to mu. Now choose u to be phi x minus y. Then what do I have? Then I have infimum over u, which is phi x minus y, and yeah, I'm worried about the denominator, but denominator, oh, that's how I get the f, right? Okay, so this is phi x minus y transpose d phi x transpose phi x minus y by phi x minus y transpose phi x minus y. And this guy should be greater than equal to mu. So I can move this guy on the right. I mean, I should not. Should I do infimum? Okay. I mean, in general, why should I infimize now? What I'm saying is that choose some y, and this must be greater than equal to that, and this guy goes there on the right. So this is phi x minus y transpose phi x minus y, and this is mu, and this is phi x minus y norm, right? So phi x minus y norm squared, and this guy here is d phi transpose phi x minus y norm. So this guy is d phi x minus y norm squared, and this is greater than equal to this. I don't know where I am here, but it seems like so this is greater than equal to mu. Yeah, I'm exactly okay up to here, and then at the end, what am I supposed to prove is, so this is our f for sure, and this is 2f. Okay, so this guy is 2fx. We can, so this is equal to 2 mu, and this is indeed equal to, also if I subtract, infimum is also fine. So this is still okay because I'm subtracting, so it's making things even lesser. Okay, so since I am subtracting something, so it's making it even lesser. And you know, infimum of f cannot be negative, right? Because it's norm. So I am subtracting something that's positive. Okay, so hence it's valid. Okay. So if you rearrange this, then you have the claim, right? That so in this case we wanted to see like how this condition here on the eigenvalues does lead to PL condition. Okay, so we can stop here. Okay. Okay. Thank you.